Okay, so I want to go over that same example again, only I'm going to do it the way the example in your book does it, which is to do the integral instead of an integral that integrates over dx from the point of view of the line. In other words, you're capturing all the charge by integrating dq up and down the line from minus infinity to infinity. Your book does it as a theta integral, imagining adding up the electric field in this point. If you're at this point, adding up the electric field due to all these contributions as you change theta, looking at the end of the line infinitely far in that direction and the end of the line infinitely far away in that direction. We'll see how the integral works in that situation. We're going to have to express all of our variables in terms of theta instead of expressing them in terms of x and r. So we set up the problem the same as before. The electric field is equal to the integral of just the x components of the electric field because the y components cancel one another out, which is equal to 1 over 4 pi epsilon naught, the integral of dq over r squared times cosine theta, where cosine theta gives us just the horizontal component of that electric field. So we want to now express this integral all in terms of, all in terms of theta and x, which is constant, instead of r and y. So the first thing we want to recognize is that r, this distance from each little bit of our charge to the point of interest here, we can write that x is equal to r cos theta. So r is equal to x over cosine theta. So we can rewrite this as 1 over 4 pi epsilon 0 integral dq of 1 over this squared, which is going to be cosine squared theta over x squared times cosine theta dq. Okay? X is a constant. We'll be able to pull that out of our integral in just a second. Now we want to talk about how do we express this dq, this little bit of charge, which remember we said was equal to dq is lambda dy. We want to express that not in terms of y, but in terms of theta. So what's the relationship between y and theta? We could write that y equals r sine theta. That won't get us very far, though, because r isn't a constant. It's better to express this as y equals x times the tangent of theta, because x is a constant. We'll be able to pull that out of our integral. You can think of this as sort of an integration by substitution, and you really only know what the right substitution is to make just from doing this kind of problem a lot. So if y is equal to x tangent theta, then dy is equal to x times d tangent theta. Derivative of tangent is secant squared, so that's 1 over cosine squared theta d theta. Okay? So this dq, which is lambda dy, we can now write as, where all this junk is down here. We've now got our electric field is equal to 1 over 4 pi epsilon naught integral cosine cubed theta. This x squared can come out front for now. Cos cubed theta times dq, which is lambda dy, where dy is this, x over cosine squared theta d theta. We've got another x that can come out. Lambda can come out. It's just a constant. So that gives us 1 over 4 pi epsilon naught lambda over x squared times the integral of cosine theta d theta. What are the limits of integration for our cosine integral? We think about integrating so that this point here sort of sees the whole line. Okay, what are our theta limits when we look infinitely far that way? If you imagine just standing at this point, if there's an infinite line in front of you, how far do you have to turn to see the end of that line? The answer is that you have to turn essentially 90 degrees that way and then 90 degrees that way to get the whole line. So our limits of integration for theta correspond to minus pi over 2 to pi over 2. Notice how much easier this integral is to do than the one we had when we did it as a y integration, which was 1 over x squared plus y squared to the 3 halves. Our integral here is actually really straightforward. What's the integral of cosine theta from minus pi over 2 to pi over 2? It's just sine theta. It's 1 minus minus 1. This integral is just 2. So the answer we get is equal to 1 over 2 pi epsilon naught. Oh, I lost an x here somewhere. This x times that x should have given us a 1 over x. It's equal to lambda, 1 over 2 pi epsilon naught lambda over x. And that is equal to the same answer we got last time. Okay, when we did it as a y integration, we got lambda over 2 pi epsilon naught times 1 over x. And we talked about the fact that the electric field is inversely proportional to the distance instead of inversely proportional to the square of the distance. So sometimes in these problems you'll be given you'll be faced with a choice as to what the right variables of integration are. And in some situations, one choice of variables will make the integration very easy, although setting up the variables to integrate might be a little bit more complicated. In some situations, setting up the variables might be straightforward, but give you an integral that's fairly complicated. And you can only know which is the case, again, just by practicing lots of problems like this. So we're going to do one more example in this batch of Chapter 21 stuff, which is to look at the electric field of, instead of a ring of charge, okay, a charged disk that has a solid distribution of charge over its area. So that will be the next video.